So continuing on, vinegar has this lovely formula. I don't think anyone's going to remember it off the top of their heads. That's the formula for vinegar. CH3COOH. And it has some really fun things to it. This is called ethanoic acid. Yeah, it's okay. This is the intro. I will explain what all of these words mean and why they apply to that formula later. This is just the intro. Now this one's even more fun. This is dynamite's formula, C7H5N3O6. That's it. This is known as trinitrotoluene. Yeah, it's going to sound like I was abducted by aliens when telling you some of these names, but this is trinitrotoluene, which is where we get our other name for dynamite. What's another name for dynamite you might know? TNT. So this is the TNT part of the dynamite name, trinitrotoluene. That's where the TNT part comes from. Now, trinitrotoluene is still a common name for dynamite. That isn't even the fancy proper name. The proper name is 2-methyl, spell it right, methyl, 1,3,5 trinitro benzene. So they get out of hand quickly. But the reason why this name, even though you can see it and it kind of sucks, this will allow you to draw it exactly. This tells you exactly where each of the molecules go, how many of each, and where they go exactly, how they're linked. All that information is given in that name. I can draw this exactly given that information. And that's what you are going to learn how to do over the course of this chapter. And the main important thing, that is the reason organic chemistry is the best thing ever, is carbon. Carbon, element number 6, is the greatest thing to organic chemistry. Its versatility is what makes all the cool things possible, specifically us and all life is carbon, and all of these things what makes it awesome. So, what makes carbon so awesome? It makes 4 bonds, specifically covalent bonds. What's a covalent bond? Yeah, that's real 10th. Actually, it's kind of 9th grade and 10th grade a little bit. What's a covalent bond? Sharing electrons is correct. They share electrons. They overlap those valence shells. It's where the valent word comes from. They share their valence electrons. Valence. Sometimes it's not very creative in chemistry class. It's really just the name, but in Latin. It forms this cool shape. It forms a tetrahedral shape. Nope. 4 sides. Tetrahedral shape. The tetrahedral shape, I'm going to slide slightly to the side here. Hopefully everyone can still see. I'm going to draw it here. So the way we draw these things is super fun. I'm going to put a C right in the middle. Now, how many dimensions does a tetrahedron have? Well, it has 4 sides. So how many dimensions is it in? It's not a square. It's in 3 dimensions. It's this 3-dimensional triangular shape. If you've ever seen a dice that has 4 sides on it, it's like 4 triangles pasted together. So that's what a tetrahedron looks like. It's 3-dimensional. We use 2-dimensional paper, so we have to come up with a fancy way of drawing 3-dimensional shapes on 2D paper. And the way we do this is with some fancy lines. We take two of those lines and put them here. That's going to be our plane of the paper. And then we draw this fancy like triangle little thing that is like showing the foreshortening, like artistically, that it would be coming out of the page at you. And then we have this other one where we draw this like dashed line as it goes away from you into the page. And on each of these lovely molecules, we will just draw an H on it. I'm just going to draw an H on it because that's usually what sticks to carbon the best. H's love sticking to carbon. Hydrogens. And so let me just add that as my asides here on the page, in case no one's listening, into the page. And this is out of the page. So that's how we draw that, because it's not like it's not four, like it's not like a flat with like north. It doesn't look like a compass. It's this three-dimensional triangular kind of shape. Speaking of that triangular shape, between each of those things is 109 degrees. If you know your geometry. So this particular angle, like between those two, that's 109 degrees. So it's not a 90 like a square would be. It's 109. And the best thing about carbon, and why we use it as an entire branch of chemistry, is it can make long chains. Carbon loves hitting another carbon, connected to another carbon, connected to another carbon, and they can get very, 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 very long. So long. Longer than we will care to want to do later. So, there are many different ways to show these kinds of compounds, like styles of drawing them. Some give more detail, some are more simple, but they all show the same molecule. So I'm going to draw ourselves a few molecules here. The first style is called structural. And that kind of shows where all the linkages are. So I'm going to draw a simple 4-carbon chain here. And so I'm going to stick 4 carbons beside each other, and each one has to have 4 bonds. So on each of them, let's put that there. On each of the carbons, there are 4 things sticking out of the carbon. And so it looks like this, and on each of them, there's a hydrogen. So many hydrogens. So that is the structural way of drawing it. Now, this isn't like an accurate picture, because this is all flattened out, and we saw from above that it's this kind of three-dimensional triangular kind of shape. And so we only draw this because it's paper and it makes sense. It just shows where all the linkages are. So we can see where each of the bonds are, as opposed to like what the shapes are in three-dimensional space. There is something called a condensed drawing. Condensed. And that's just jamming each of the groups together. So we're basically going to take the first carbon group, and I say, it's a carbon, and it has 3 hydrogens stuck to it. What's the next carbon? How many hydrogens are stuck to the second one? 2. So that is CH2. How many carbons are stuck to the next hydrogen? A CH2 again. And then what else is left? No. 3 again. So we can count. This is how many hydrogens now? 10? 10. Okay, so 10 hydrogens altogether. The last one is called a line diagram. So this is the simplest and tries to ignore all of the extra information, but sometimes can be hard to understand, but it's very simple and easy. This one looks like this. No, that's it. That's the whole diagram. That's the whole diagram. This fully encapsulates this molecule. Basically, each of these parts, now I'm drawing them with dots, you don't have to draw them with dots, but each of those represents a carbon, right? And we're basically ignoring all the hydrogens and as default. It's default full of hydrogens because carbon has to be full. Carbon can't hang out just with empty spaces. That's how chemical reactions work. Chemicals like to be full. So if I leave everything blank, I'm assuming all the hydrogens are there too. And if I have to put something else on because something not a hydrogen is stuck there, I just add the things that aren't hydrogens into the diagram and basically see if it's blank, that means it's hydrogens that are left over. So that's the shortcut diagram. And this is very useful when they're really, really big. The structural diagram gets really annoying the bigger and bigger the molecules get. But it is very clear. You're not going to get messed up with those. So the line diagram is the easy one. And you want to try to use this zigzaggy pattern because this is the 109-degree angle that's showing how they actually kind of work together. So that's why we do a zigzag. So the line diagram doesn't work if you draw it as a straight line. That will not work. You got to go up and down every time we do a different molecule. Our very first type of compound. The first class of compound is called alkanes. So this is the alkane group of chemicals. They are what we call I don't want this color. Let's go back. Saturated hydrocarbon. Whoops. Hydrocarbon. So we're going to have a couple of words here that I have to define. Both of them. Hydrocarbon is a compound that is full of carbon and hydrogens. And saturated means it's full. It's full. There's no missing pieces. So it's only single bonds with carbon. This leads you to believe that there are things that aren't single bonds, and we'll get to those later. But for now, single bonds only. Cool things is the bonds can freely rotate. Bonds can freely rotate. So, as shown in my little diagram over here, you can see that these carbon bonds, they can spin along their axis. They're not locked into place. They can kind of spin and turn. They're not like a fixed, rigid thing. They're very flowy. They can kind of bend. The longer they are, they can kind of, they're flexible. There's flexible in them. They can be substituted. In other words, we can take a hydrogen off and put another element on there, like chlorine or bromine, or, I got periodic tables here too, so I'm not lost. It's not as big as the other one, but we still got periodic tables up on the wall. So you can put other compounds in those places, take away an H here, and put something else there. They can do this fun thing. They can be cyclical. They can form rings. So because they're flexible, they can kind of come back and make a complete ring, and there's still this alkanes structure. And when we name them, they have a common suffix. Getting our English language skills up to date, and it's called ane. So we name them with the alt end in ane. So whenever we call a compound, we have it ends in ane. Are there any anes you know of? Propane is one. It's absolutely one. That's not one. We'll go through what they are. Here's some common ones. This is how they start. When you have only one carbon, one by itself, so you have a carbon and then the rest is just hydrogen. Yes?
Sorry, what does that word say?
Where?
Can be
Cyclical. Like a circle. Like a bicycle. Cyclical. And here's going to be where everyone usually kind of giggles a bit. The first one is called meth. Yeah. Basically, it's the prefix for a single carbon. So whenever there's a compound that has a single carbon in a group, it has the meth word attached to it. So one carbon with a bunch of hydrogen stuck to it is called methane. But you knew that. You knew what methane was. Two carbons is eth. 3 is prop, not prop, prop. I know. I'm going to mess with this because that's for the propane. And then we have this one, which isn't but, it is bute. It's bute because butane is a thing. And then the rest ones are more common. You will have seen these ones before. It's pent, hex, hept, oct. All the normal ones now. Non, deck, undeck, and dodeck. So not do-deck, do-deck. So those are about it. Any more than that will get out of hand, and we definitely don't do that. 12 carbons is a lot of carbons. So we tend to not have, that's huge. Massive. So those are our prefixes. So we're going to draw a few of these lovely compounds. I'll leave this right there. Hopefully I can get it all on the same page. So I want to see methane. And then we're going to do ethane and propane. And so we're going to get practice with drawing each of these particular compounds in the 3 styles. So structural shows where the bonds are. So you might have to write kind of small. That is C with the 4 H's around it. That's the structural diagram for methane. Condensed is pretty easy. It's just CH4. And the line one is super boring. It's a dot. Very boring. We never use the line diagram for methane because it's dumb. Next one. Ethane. 2 carbons stuck together and then filled up with... Oh, that's actually my phone. I was like, whose phone is ringing? Mine. Hello. Okay. He's not here. No. I don't know. Yeah, sorry. He's not here. Okay, bye. That's funny. Okay, next. Back to what we're doing here. Oh, that's going to be fun later. Fill it with hydrogens. And then this one is not that bad. So we fill it with hydrogens. There's 6 around. The first one has 3, and the next one has 3. So that's our condensed form, where we just list our molecule in this way. And then the last one is this. So it's a good habit to get into, to draw it at a little bit of an angle, like you would draw the next one down from it, as opposed to drawing it straight I know it technically doesn't matter, but it's a good habit to get into, to draw it up a bit to show that that's... Oh. It'll make more sense when we draw the rest of them. Propane has 3 carbons stuck together. 1, 2, 3. 1, 2, 3. Lots of lines everywhere. H, 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 H. Getting really tired of H's in so many ways that a lot of the structural diagrams will show you just a line up and then skip the H part, and we're just going to assume that the end is an H because it's normally an H, and if it's not an H, we'll tell you when it's not an H. It's like it's an omission, I guess we'll call it. This one is similar to the one we did in our example. CH3, CH2, CH3. And the line diagram is one of those. Clearish? All right. See how good you guys are doing by doing the next 2, 4s and 5s. You might need to write kind of small for the condensed for the 4s and 5s. The rules start based on the longest chain. So the longest chain will be, if there's branches off it, we just pick the longest one, and that's the base name. Then we start numbering that chain, starting closest to any groups. Groups. So that the numbers are the lowest number. So if we can think about a 5-carbon chain and there's something stuck on the second carbon, that's same as being the 4th one. We will choose the number 2 because it's smaller than 4 because it's the same on both sides. We have to name, so we say what each of the groups are and give the location, what number. The location of each group by number.
Pardon the interruption. Would staff Phyllis Cruz please come to the office for a message?
Okay. So when 2 or more groups are on the list, put them in alphabetical order. So when we have 2 different groups we want to add, which one gets first in the name is the alphabetical order one. And then we are going to, when there's more of them, we put the di, the tri, the penta, all the fancy prefixes that you guys know from last year. And these prefixes don't affect the alphabetical order. Count. For alphabetical order. They don't count for that. So if we call it like a trimethyl group, the M for methyl group is what we're looking for, not the T for tri. I am blowing through this, guys. This is going to be fun. All right. Let's start small and name this lovely looking thing. The first thing we want to go is, I'm just going to list my ideas out so we can kind of keep track and follow the pattern. So the first one is the parent chain. What is the longest chain? If I count up my carbons, I got 1, 2, 3, 4, 1, 2, 3, 4. So it doesn't matter because these 2 on the ends are going to be the same. So the longest parent is 4. So this will be a butane kind of molecule. There'll be things added to it, but it starts with being a butane. And let's just say, for clarity, this is the one added to it, right? We'll start with the base and say this one on top is the added group. So using this parent chain, we're going to number each of the carbons. And we could start from this end and start with 1, 2, 3, 4, or we can go the other way, 1, 2, 3, 4. Which way is determined by which numbers would be the smallest. If I start here, this one gets a 2. So we'll do it that way. If I go the other one, this one becomes a 3, and we don't want the higher numbers. We want lower numbers. So we're going to number this one 1, 2, 3, and 4. So these are the number of carbons in each chain, so we can tell where that group is. So we have the group, pen here. So the group of 1 carbon. So that's the green one I've circled here. It's a group that has 1 carbon in it. So it gets called methyl. So we put this little YL sounding ending on our group names. And then we go, it's on carbon 2. So, oops, that's not a very good looking 2. Let's fix it. So it's on carbon 2. So these are the things we need for our name. The good news, 1 group, so we don't need to worry about the alphabetical order. 1 place, so we only need 1 number. And so the answer to this particular molecule's name is going to be 2-methyl butane. So that's going to be the name of this particular molecule. It is a butane chain with a methyl group on carbon 2. So we think about it kind of backwards the way we construct them. We look, okay, it's a butane. I got a 4 carbon chain. A methyl group. I have a single carbon group stuck on the 2nd carbon. That's how that goes. All right, we're going to get bigger. Notice it got real big real fast. I don't know how well it showed up here. It's a little blurry. Looks like it's a lot of blurry. Let's see if I can fix it. Basically, it numbers the carbons for us. We can, if you can read that, that's 1, pen on. 1, 2, 3, 4, 5, 6, 7. So just kind of wrote on top of them. That's just numbering our carbons. So, since this was already numbered for us, what's our base, Bo? Why do they label them like that? Because that's the longest continuous chain. If I can draw this on here nicely. Yeah, this one. This is the longest single chain. Does that clear up where it is? It's hard to see sometimes, and it's often a trial and error to see which continuous line actually gives me the longest number. So I can see that I'm going to have 2 little groups on each side. That's kind of too dark. Let me lighten that up. Just one there and one there. So those are my 2 little groups stuck to the other outside. So I can see the green is my main chunk, and I have 2 little groups stuck to the outside. And because these are flexible and can kind of spin around a bit, the way they're written isn't always in a perfectly straight line. But if you have to draw them easy in a straight line. Don't loop them on purpose. That just makes it more confusing for no reason. But textbooks and questions, etc., will give you confusing ones to challenge you, basically. So, what's the parent chain? Oops, turn the highlighter off. Yeah, parent is 7. So what's that name? Heptane. So it's going to be a heptane molecule. What's stuck to it? What groups do we have? 2 methyl groups. No. So we have 2 different single groups. An ethyl group would be a 2 carbon chain stuck onto a longer chain. So each group would have to have 2 in it. each of these groups each have one. So they're two different methyl groups. And what we will do, we call this dimethyl. In other words, two methyl groups. Dimethyl. Where are they? On which two carbons? We have one of them here on carbon 3. This one here is stuck to this one, and the other one stuck to this one. So they are on 3 and 4. So one of the ones is on 3, and the other one is on 4. So overall, my name becomes 3,4-dimethyl heptane. All right, see if you can try this one. I'm going to let you guys take a second and try this one. I'll leave those two up right there. You have the names on the top of the page. Let's take a look and see if we can draw 3-ethyl pentane. So, same idea. We're going to list the things we need to include. So, the parent is how big? Pentane is how many carbons? It's 5 carbons. So there are 5 carbons in the main chain. And we have how many groups? How many groups? Just one group, right? There's only one extra group. So we have one ethyl group. How many carbons does an ethyl group have? 2 carbons. So there are 2 carbons in one ethyl group. Where is the ethyl group? On the 3, right? So one ethyl group on 3 or third carbon. I'm going to keep it there. Carbon. So that's all the information we need. We're going to do the structural formula because I told you how to draw it. Which one is that? That's the biggest one, right? That's the C's with the lines on it. Right? So we're going to draw, because all the other ones were structural too. Actually, some of them were condensed. But structural, C, 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 and C. I always like doing it straight, but they can bend all they want, but there's no reason to get out of hand. Right? So I have my carbons, 1 through 5. I don't want to add anything else until I do my group. And so 3 is very easy. Which one is 3?
The middle one.
The middle one. So it doesn't matter what side I go on. It's the same both ways. And so I've got to add 2 carbons there. If you go on the top, that's the same. I went on the bottom because that happened to be where I had empty space to draw. But that's how I would draw this. And now that I think I've got 5 carbons in my parent chain, I've got my 2 carbon ethyl group stuck to carbon 3, I will then fill in the rest of my dashes and go, oh, I need a little bit more there. Finish those all up. Just to make sure every carbon has 4. And then I'm finished. Let's do our next one. Let me just draw this. This is my ethyl group here. There, that matches now. So, equally good is if I did, like, this is my 5 chain and that's my ethyl group. Or this is my 5 chain and that's my ethyl group. They're all the same. Because this is all just one molecule and it's all the same molecule. So, we're going to do the next one. 3-ethyl 2-methyl heptane. It's a heck of a mouthful, but we just start at the base. What is the parent? Yes, the parent is 7 carbon. We have 1 ethyl group. on 3 and 1 methyl group on 2. So those are all the things that we have. We can now draw our base. So my base is going to be 7. I'm just going to go straight left to right. C, 1, 2, 3, 4, 5, 6, 7. Whew. All right, so those are the base chain. I then am going to put my groups on after. So on carbon 2, I've got a single methyl. I'll put that there. And then I will put this ethyl group on here. Now, it doesn't matter whether you go left or right here. This is going to be the same. I've got methyl on 2, ethyl on 3, and I will now fill in the rest. Cool. Lots going on there. Jaden. Yeah. Got one more. See if you guys can do it. It's big, but you got this. I believe in you. One more. 4-ethyl, 3,3-dimethyl, 5-propyl octane. It's just a lot of carbons, but if you start at the parent and add your groups, you will get the question right. It's actually quite satisfying getting these questions right. They're like the big exponential questions. You can take something big and make sense out of it. So just start at the back and go from the parent, go to the groups. What is the 3 at the end of the ethyl? The 3 isn't for the end of the ethyl. The 3s are both for the methyls. So the numbers are in front. So let me see if I was like, the 4 matches the ethyl and the 3,3-dimethyl is a chunk. So it's kind of like, let me see if I can throw this up here. This is a chunk, this is the next chunk, that's a chunk, and then that's the base there. So there are 4 different pieces to work with here. Base and 3 sets of groups. Got lots of space so we can work with it. So I'm going to draw this side one here. Oh yeah, I was going to make you see after. So parent is 8 carbon, 1 ethyl on, what's up? It's 3,3-dimethyl. What does that think it means? How many methyl groups are there? 2. Where are they? Ethyl. Oh, so you got all kind of screwed up. Ethyl on 4. 2 methyl on 3 and 1 propyl on 5. Yeah. There are. I have actually a worksheet that I'm mostly going to make you do. I don't know if we'll get to the next one later. We got this. It's going to be 2, 3, 4, 5, 6, 7, 8. Instead of writing the last C, I wrote 8. Okay, next. What do I got here? And this is why we hate all those H's. Because these compounds get very large. Okay, 8 chain. One ethyl on 4 methyl on 3. Maybe. Okay. All right, I have finished mine. And let's see if you guys got it. I think it looks like this. But follow the steps because there are many kind of different orientations. There's a lot of carbon going on. So I'll kind of explain my thoughts through this. I started with my base straight across the middle, 8. You can make the base in whatever shape you want, but I would suggest flat. And then I just basically went across it. I've got 2 different methyl groups. Both of them are on 3. That was the 3,3 part. So there's 2 methyl groups. Both of them are on 3. I get an ethyl group on 4. That's this one here. And my propyl group is on 4. And I only did that because 3 straight up would have hit my lines. So I kind of did a zigzag for my propyl group. All that matters with a propyl group is 3 carbons. That's all that matters. I did a little zigzag to fit it in my page. And that's it. That's the pieces that we had. We have our parent chain, 2 methyls, an ethyl, and a propyl. Questions?